All right, thanks everybody for coming. This is the last session of the first day of QIP, so another big, a long day full of really excellent talks, and we'll top it off with a little bit of a casual evening. So we're going to introduce a little bit of software, talk a little bit about practical quantum programming, also to introduce us and ourselves. So thanks for coming, and we're really looking forward to talking more with you guys. So I'll just introduce who'll be speaking. It'll be me and two of my colleagues today. So my name is Will Zhang. I'm the software and applications lead at a startup called Rigetti Computing. My background is a real mix of hardware and software in quantum computing. So I started in superconducting circuits and superconducting qubits, messing around calibrating transmons in the lab. And then it seemed like transmons were eventually going to get built and scaled up, and we're still working on that. But so I switched and did my PhD in quantum algorithms in CS, actually all the way in category theory in quantum algorithms. So my background goes from calibrating qubits in the lab to category theory for quantum algorithms. And it's been a really fun journey, and that kind of spread has given a little bit of a view to some of the stuff we'll talk about today. And my colleagues who will also be speaking are Robert Smith and Nick Rubin, who will introduce themselves when they come on. So we've already had 20 great years of progress in quantum computing, both in hardware and in software. From the first original error-correcting codes, first original qubits, things in NMR, the first kind of round of quantum algorithms that everybody knows, Shor's algorithms, Grove algorithm, and all these kind of things. But what's been happening recently has also been very, very exciting. And there's been two kinds of shifts that have been very important for the field, and in particular for the stuff that we do and the things that we focus on. One of those is that certain implementations of quantum bits, in particular superconducting qubits, have gotten good enough that it makes sense to try and scale them up and to do more complicated kinds of algorithms in an experimental way with them. The second big shift is a change on the algorithms and software side. So as of 5 or 6 years ago, when you do back-of-the-envelope calculations for things like Shor's, you end up with million-gate, fully fault-tolerant, error-corrected algorithms. This kind of performance will take a long time to get with hardware. But more recently, there's been an emergence of things that, for the purposes of this talk, I will call quantum classical hybrid algorithms. Quantum error correction actually itself is a little bit like this, where there's classical processes doing decoding and also quantum measurements and parity checks. But there have also been ways of doing quantum simulation of systems, ways of doing optimization algorithms that have come about. And in particular, there's been some ways of maybe showing quantum supremacy in near-term devices. There's going to be a talk about this on Friday that I really encourage you guys to attend. Sergio is giving it from the Google group. That has given some evidence to the idea that actually with 50 to 100 noisy qubits, we might be able to demonstrate quantum supremacy for a couple interesting problems. We might be able to start to try and do some interesting quantum simulations, even with some noise. So this is a really, really exciting time to be working in quantum computing. So I'll talk about us. So Rigetti's a venture-backed startup. It's based in Berkeley, California. There's really 4 key beliefs that come together, and that are the things we focus on. So we work with superconducting microwave circuits. We're trying to scale them up, make them bigger, make them better, make them more performant. We're focused on near-term applications. So we're not waiting until having a very, very large fault-tolerant machine. We're trying to see what we can do while we still have physical qubits, while we still have a bit of noise. So in particular, that means things like variational quantum eigensolvers, Quil, the quantum optimization algorithm, and also obviously testing quantum error correction. So building towards fault tolerance is part of that. And then fourthly, there's a lot of people talk about this, and we're taking it seriously as well. We think that maybe the first quantum computers will be coprocessors that you access over the cloud. And so that's sort of the model that we have in mind, and you'll see that in the software that we're actually talking about and launching today. So the company itself, so one of the picture in the top left, I guess I should describe this. We're at a theory conference. That's a superconducting circuit chip. And to make it, we've had to build up a team of about a little more than 50 people across fabrication, quantum engineering, which for us is designing superconducting circuits and also testing them and calibrating them. Also doing work in the cryogenic systems and the control electronics that are involved here. And then finally, in the fourth bucket, the quantum software and applications team, a lot of whom are actually here at QIP, and of which I'm a member. The last, of course, plug is we're still growing and we're hiring, so anyone who wants to talk to me about that, we have a booth outside, or just grab any other Rigetti people. So I think to focus what we're talking about today, there's been a lot of advances in quantum algorithms. There's been a lot of advances in chips, and now there's a need for software tools to help us investigate the next phase of quantum computing. Quantum circuits are great, though they are typically programmed in LaTeX. They do not scale that well to the kind of large and complex things we really want to run on stuff that we're going to have in the next 3 to 5 years. This is recognized. It's actually been recognized for a while, but it's starting to, I think, really, really matter. So there have been some research and academic projects, things in C, Haskell, Quipper. Dave Wecker tomorrow will be talking about Liquid, Microsoft's excellent toolkit in F#, which uses a lot of the sort of multifaceted things in that language to do interesting things. And there's another kind of bucket of software that's also worth talking about, which are tools that some theorists and modeling people use, a lot of them in Python, like Qtip, Qinfer, which Chris is talking about. There's a poster number 63 in that room if you want to learn about Qinfer. It's for Bayesian inference. And things like a Python package that does gate set tomography for you to help you calibrate your chips. So there's a little bit of an ecosystem of software tools that are starting to grow. And I think this is really, really important as we start to move into the next phase and start to care not just about the scaling of algorithms, but what the actual gate count is, on which qubits they are applied, how we compile them, and how they'll perform. So this is very, very early days, and I want to just kind of throw out one more thing. There also needs to be more foundational research, and one thing that we're also announcing today, what we're really excited about, is you guys might know Peter Selinger. His group did a lot of the foundational work on Quipper, a lot of circuit compilation algorithms, and one thing that we're doing is we're actually funding a postdoc with Peter. If you'd like to work on the foundations of quantum programming languages, he's working on something called ProtoClipper, kind of really looking at the foundations of QPLs from the ground up. Send him an email, because he's got a postdoc position, and you can talk to me about that or him. So these are really early days for thinking about what it means to practically program a quantum computer. And I want to introduce Forest, which is our internal toolkit. So this is all in draft. I really think we should think about high-level languages. We should think about instruction set architectures, everything from the bottom to the top, but it's all really in draft. It's not like we can sit down and write down a spec for what's needed to program quantum computers in the next 3 to 5 years, but we should take a start. And so this is one draft that we've been using internally, and there's a few parts to it. So as I mentioned, it takes seriously this idea that a lot of people have about the coprocessor model, about the cloud access coprocessor model. So there's a couple pieces of software on the client side. I'll go through them quickly. So the first is a quantum instruction language called Quill. We'll talk more about that. Built on top of that are some Python libraries called PyQuil, which lets you generate these circuits and run them. And then on top of that, there are some examples in a repo that we're calling Grove, where we've looked at some of the near-term algorithms that we've internally studied and that we'd like a lot more people to work with and add things there. So this then runs in a client-server model on either a quantum virtual machine, which is our name for a simulator that takes in Quill code and simulates the action of a quantum processor, or on a real quantum computer. So we've released this a few days ago. The website is forest.rigetti.com. It's a toolkit and an API for experimental quantum programming. I'm really excited about starting to make it available. So what this concretely means is that everything in the top bucket and that client side is all open source on GitHub under the Apache v2 license. And there's all the documentation is hosted on Read the Docs. You can check that out there. You can pip install it. We'll talk more about this stuff soon. And it also means that the server side, which we're still working on a lot, is now open for private beta quantum virtual machine signups. And you can sign up on forest.rigetti.com to get a key to work with that. So the idea is that, and these are the things that we've used Forest for, basically. The idea is that Forest helps you write quantum algorithms, study quantum algorithms, and program quantum hardware. So internally, we've done everything from writing VQE examples and instances to kind of extending them in some particular ways, to studying quantum algorithms under noise, studying how things like these quantum supremacy results will vary under different kinds of device connectivities and gate sets and architectures, and also to really run Quill code on superconducting quantum chips. This is a lot, and it's more than any one team of researchers can do, and it's more than we can do in one go. There's so much to do that we're really excited to make this available to the community to play with and kind of build on this next draft as we all try to get together to really get to a place where we have tools to do these things. So the quick overview for what the workshop will be today, again, it's pretty informal. So Robert will hop on and give a quick overview of Quill itself, the sort of pseudo-spec for the language, and the quantum abstract machine, which is the mathematical structure that Quill targets. Then I will run some quantum circuits on a superconducting qubit, because that's always fun. And then Nick will hop on and talk a little bit about the Python libraries that we have built on top of PyQuil in a couple different areas that we think are really important for near-term quantum programming. Then we'll break up. There'll be drinks, demos. We'll have Jupyter notebooks. You guys can play in the environments, play with the software, break it, all those sort of fun things. And we'll talk about the Quill bot later. So I'm happy to introduce my colleague Robert, who'll talk a little bit about Quill and the quantum abstract machine that it targets.
Hello, everyone. My name's Robert Smith. I work as a compiler engineer at Rigetti Computing. One perhaps interesting thing about me is that I don't actually have a quantum background. So my background is more in software engineering and sort of mathematical and mathematical software and experimental mathematics. And coming to Rigetti has been interesting, kind of getting my toes wet with quantum computing and kind of having a perspective of quantum computing that is really software oriented. So I want to talk a little bit about Quill and the quantum abstract machine, which is kind of the basis for a lot of the tools that we've built. So Quill is kind of first and foremost a very portable description of classical quantum computations that can target really sort of any machine, any gate-based universal machine. Not necessarily superconducting qubits, although that's of course what we work with. But it doesn't target our hardware in particular. It's portable across really any platform. Quill is also foundational. So what I mean by this is that Quill doesn't actually try to encapsulate every single possible abstraction that has been developed in the quantum computing community. So for example, things like circuit reversal or the construction of oracles or gate compilation or so on and so forth aren't actually included in the Quill language itself, but rather these are tools that you can build on top of Quill, and Quill will sort of always provide a stable foundation for that. The most important bit about Quill, maybe second to its portability, is the fact that it's a hybrid language. Classical quantum hybrid language. And so the best way I think to describe this is actually through something we're all familiar with, which is a circuit. Here I have a circuit for quantum teleportation. And quantum teleportation, of course, has these quantum bits to it with Hadamard gates and CNOT gates and so on, measurement. But there's a part of the circuit which is a little less well-defined. These measurements in the classical bits, and something happens with these bits, but the circuits don't really make that well-defined. And so Quill makes this well-defined, and I'll talk about that shortly. First, I want to delve into the sort of abstract programming model of Quill. Not really the practical way to view Quill, but kind of the theoretical foundations that allow you to really understand what's happening under the hood. So Quill is really a syntax for something called the quantum abstract machine, which is just a purely mathematical device that consists of some state. And Quill is a syntax for instructions that transition on this state. So there are really three types of states that the quantum abstract machine has. There's the quantum state, of course, your set of qubits or your wave function. There's the classical state, which is just a set of bits. And then the execution state. What I mean by that is when you're going through a program, there needs to be some notion of sort of where you are in the program, and that's encapsulated by this state. People familiar with just normal CPUs might be familiar with the idea of a program counter. That's a very similar concept here. On the right, I have an example Quill program, a Hadamard on qubit 3, a measurement of qubit 3 into a classical bit numbered 4, and then a jump instruction jumping to a label called end, depending on the value of a classical bit. And I want to walk through this program and talk a little bit about how that affects the quantum abstract machine's state. So the state consists of this quantum state psi, classical state C, and execution state kappa. And the quantum abstract machine always starts off in a 0 state. The quantum state is a 0 state. The classical bits are all 0. And the program counter execution state starts off, of course, at the start of your program. So we kind of see that in that first starting box there. And after we execute a Hadamard on qubit 3, of course, the quantum state is going to change. Or if Hadamard on any qubit is going to change the state. So we see there, I have a little red circle around psi, and psi 0 has become psi 1, indicating that it's changed state. I didn't put a circle around the kappa there, although when you change instruction, of course, the instruction counter is going to increment, but it's a sort of trivial change of the instruction counter. So I'm just ignoring it in the first diagram. If we move on to the measure, this is a much more interesting instruction. One, it's a classical quantum instruction, meaning it's an instruction that affects the quantum state, but it gives us feedback and allows us to sort of observe its results by way of the classical memory. So here, because it's non-deterministic, we may measure the qubit as a 0 or a 1. And so we get this branching structure in the state. If we measure 0, then we'll deposit that in the classical memory in classical bit number 4, in which case nothing has really changed because everything started as 0. Or in the case that we measure 1, we deposit that in address 4, and the classical state does change. So you can see that marked on both circles, that both classical and quantum state are changing. The last part, and this is a very different feature provided by Quil that I think is very unlike a lot of other sort of quantum languages out there, which is a sort of native support for classical control. So here I'm saying that I want to jump to a particular part of a program depending on whether the value at address 5 in our classical memory is 0 or 1. So in this case, the jump when instruction, there are other jump instructions, but jump when says jump to the end when address 5 contains the 1 bit or true value. And as such, we can see in the diagram that kappa changes if we jump, or kappa will just increment if the bit is 0. This is, like I said, just a very convenient way of thinking about the abstract machine, and it's kind of something that should kind of be in the back of your mind when you program Quil. But I actually want to go through a sort of more practical example that talks about the strengths of Quil as a practical language for doing computations. So here I have a sort of cartoon of a quantum processor with some instructions to execute, and on the bottom I have some classical memory. There are two cells there that don't have a number. You can think of them as having 0, but just for illustrative purposes, I emptied them because we're going to change the memory there. If we iterate through this program, Hadamard on 0, C naught of 0, 1, constructing a Bell state, that's going to change the quantum memory. But then we do a measurement on these qubits, qubit 0 and qubit 1. We're going to deposit them in the classical memory. So we see here, when you do a measure qubit 0 into classical address 7, we've deposited it, in this case, we measured a 1, and we've deposited that in the classical memory. Being a Bell state, of course, if we measure qubit 1, we should get the same result, and indeed we see that we have that. And then we have this last instruction called wait. This isn't a very computer scientific instruction in the sense that it doesn't really have some nice semantics. It's just a more practical device for synchronizing your quantum computations with your classical computer. So wait actually says to stop or halt computation on the quantum computer and transfer control to your classical processor. So our classical processor is using the quantum processor as a coprocessor, and computation can resume on the classical processor. There are lots of different ways this can be implemented, depending on the implementation of the quantum processor. It could be implemented with interrupts or some other mechanism. But whatever the mechanism, we transfer control over to the classical processor, and the classical processor itself can access memory. That is, in particular, this classical memory. So we see here we're doing in this sort of pseudo Python code, if the bit at 3 plus the bit at 7, if the sum of those is 2, then maybe we set some theta parameter because we're doing some VQE loop or something like that. And we can do any classical processing based off of that data. And furthermore, we can set data back in those classical registers for the quantum processor to use. So in this case, the quantum processor and the classical processor sort of have this symbiotic computational relationship. And as the computation sort of evolves, both can help one another where either of them is better. I won't belabor the formal details of everything. We have a white paper that is updated. I don't know if it has reached the archive quite yet. If it hasn't, it should be, by the end of this week, which you can find there, Practical Quantum Instruction Set Architecture. It goes through all the mathematical details of the instruction set and the semantics of each instruction and a little bit about practical implementation of the machine, especially as the way Rigetti has implemented it. I want to cap off and actually go through and go back to that circuit that I showed at the start of my section, which is the classical or the quantum teleportation circuit, which you can find in any textbook, and kind of go through how that actually would manifest itself in the Quill programming language. So here I have this def circuit. Def circuit in Quill is a construction to kind of make reusable functions in some sense. So def circuit, teleport A, Q, and B. That says that it takes 3 qubits as arguments. And we can later instantiate it, as you see at the bottom, teleport 0, 1, and 5 if we're doing a quantum teleportation with qubits 0, 1, and 5. So Alice's ancilla is labeled Q here. Alice's qubit is A, and Bob's qubit is B. And there's sort of 3 logical sections to this circuit. There's a construction of the Bell state, which we can kind of see this correspondence here. Very sort of direct translation. There's the measurements, which is the actual sort of teleportation part, which is a construction of another pair, Bell pair with the ancilla, and then the measurements. But I want to pause here and say that the measurements aren't just these, they're not just measurements. They're measurements whose results are being deposited back into this classical memory, which is why I've annotated the circuit up there, the little measure boxes with 0 and 1. We're saying when we measure this, deposit the result in address 0, and when we measure Alice's qubit, deposit the result in address 1. This becomes useful for the third part, which is a sort of generalization of what the circuit actually provides. So here, in order to implement sort of classically controlled gates, instead of making a dedicated functionality in the Quill language for the notion of a classically controlled gate, instead we use the concept of control flow, classical control flow within Quill to supersede that notion. So here you can see that we can skip the X gate on Bob's qubit or skip the Z gate on Bob's qubit, depending on whether the bit in address 1 or address 0 is 1 or 0. So the last thing to sort of iterate about this is that the classical control is actually arbitrary. So here we've superseded the notion of a classically controlled gate using a jump, but in fact we can jump anywhere in the program. We can have sort of all of these notions that we get for free in classical computation, like loops and branching and so on, as the same in our quantum program. And this is something that can be implemented efficiently in a quantum processor, especially with the help of technologies like FPGAs and so on. So I'd actually like to move and just show a couple examples of Quill actually running, just to kind of solidify the points. So here I have a notebook right here that is a Jupyter notebook, but we've modified it to actually run Quill. So it does not run Python code here, it runs just straight Quill code. And this is something that people will be able to play with afterwards. So I'm not going to go through the entirety of the notebook, but I want to show a couple examples. If we execute this identity gate on qubit 0, of course nothing should happen. And we see that the wave function remains in the 0 state. The amplitudes of the wave function are in typical sort of lexicographic ordering of the basis elements. And classical memory itself hasn't changed. We haven't done any measurements. We haven't done anything to actually change the memory. To give a little more complicated example that's not too complicated, an X gate on 0. This has the act of kind of flipping to the opposite pole on the block sphere. So we see our wave function has changed to be in the 1 state. We can do, of course, multiple gates. We can demonstrate measurement. If we flip to the opposite pole of the block sphere, we see, and we do a measurement on that qubit into address 0, we see that we indeed got a 1 as our first qubit. Something that's important here is that when we measure a qubit, we are doing a projective operation, but the state of that qubit actually is maintained through computation. So the qubit isn't reset or anything like that. If you project into the one state, for example, the qubit will stay in the one state for as long as you don't, perform further operations on it. And I think this is another differentiator from, for example, the circuit diagram, where it sort of implies that this qubit somehow turns into a bit. But here in Quill, the qubit stays a qubit, and you can further modify its state. Its measurement is just recorded in classical memory. I'll skip down and show an example of a bell pair, a Hadamard on qubit 0 and a C0 on 0 and 1. We see here, if you look at the wave function, the first element and the last element have equal probability. If you square those and everything, you'll get 50%. And we didn't have any measurements here, so our classical memory stays at 0. We can define new gates. You can see the definition of a sort of simple gate right here, this negative Hadamard. Another more complex gate definition, a gate that's actually parameterized by some parameter. Here we have a rotation gate, an X rotation parameterized by theta, which is built in, but just for demonstration purposes, it's here. And then the construction of circuits, which I showed you. And then this last example is one where we have this control flow. So if we look here, we're jumping depending on this sort of first line here, jumping to label 1 depending on the value in classical address 0. Since it's 0 in its state, it's going to not jump. But if we intentionally use the true instruction in Quill, which just changes the classical memory to a 1 bit. It's sort of, it's a constant function that forces a classical address to be 1. Then that jump will be taken, and we see that the classical memory has a 1 bit in the second element. So this is just to provide a little taste of Quill, but I actually want to give the stage back to Will to perhaps show a more interesting use of Quill.
All right. So it's good. Slow. I got the foundations right, so we can pick up a little bit and do two things at once next. So I'm just going to talk a little bit more about using Python and PyQuil to generate Quill code, and I'm going to do it in the context of running on a real qubit. So what's going to happen now in this demo is we're going to go from a piece of PyQuil code in Python in a Jupyter notebook. That itself is going to compile down into Quill code, into little instructions that are then going to be compiled into waveforms that go down into the bottom of a dilution refrigerator that run on a superconducting circuit chip back in Berkeley. In particular, this one in this fridge, one of our fridges in Berkeley, this is the chip with a little bit of stuff blurred, and that's the qubit that we're going to run on. So what we're going to do with PyQuil is we're going to build up to running state tomography on this qubit. Just jump into the notebook. So the first two things we're going to do here, again, here's the picture. We're going to import from PyQuil, so this is what you would pip install, the forest connection library. You'd import this thing called a program object. I'll talk about that. You'll import some nice gates that we have as standard, and this is just for printing. So then we'll connect to our current device. We're still working on it. It's got a few bugs. And then you just build a program. So in this case, we'll build two programs. One has the identity gate, one the X gate, and we can run them on the QPU in Berkeley and get back just the index of the qubit and then the thresholded state that we get back, which matches. So what we're doing here is we're constructing a Python object, this PyQuil sort of program object, which then outputs into Quill. And so this is nice because we can manipulate the program object separately from the program that's running. We can do things like compilation on it, and we have the full advantage of everything you can do in Python to mess with the program before outputting into the intermediate representation. So a couple interesting examples that are sort of more specific to running on real hardware are throwing in arguments like turning off the thresholding when you apply a x half. So this is an Rx pi over 2 rotation going into the middle of the block sphere. And if I don't threshold, this is sort of the percentage chance of it being in the excited state, a little bit off from 50-50. But there's also other things that you would imagine getting back from a real superconducting qubit circuit, and that people will actually, I think, play with, and that we would like to encourage people to think about what they would do if they had access to this extra data. So things like the real physical amplitudes and phases, the covariance matrices, and the kind of things that come out that aren't just thresholded bits. So we're going to use Quill now to run some Rabi oscillations with some parameterized programs. So Rabi oscillations are, just iterating through a series of Rx rotations of different angles. So I'm going to construct a list of those programs, starting with, minus pi to pi, so 15 of them. Each of these is just taking from the standard gate library some Ry. These are parameterized by some theta, and then you just pass in some target qubit. Build them up into a Python list, which is what we have here, et cetera. And then running them on the QPU is just iterating through each of the programs. And in this case, I want the raw data to come back, because I'm going to actually show and plot it against amplitudes, not plot it against 0 or 1. And then we can just plot. So this is, starting at minus pi on the Bloch sphere, moving, starting in the excited state, moving down to the ground state, and then looping back up. And if this were to continue, this would just be Rabi oscillations. So we can look at measurement physics in the IQ plane. And this is fun to kind of talk to theorists about a little bit. So when you measure a superconducting circuit, when you measure a real qubit, you don't just get back a bit. You get back, like I was showing there, some amplitude and some phase, and you can sort of look at what the clusters that those form, which are then what we threshold to turn into bit values. So in this example, I'm running 10 programs that are just the identity gate on this qubit, and 10 that are just the X gate on this qubit. Oops. Almost done. 9, 10, and woo! This is what you get for the live demo. Anybody? Somebody diagnose. What's going on here? Anything? So this is a switching behavior. So we actually have sort of 3 pseudo clusters here. So the bottom one is the ground state, and then these 2 pink ones are what happens when I apply the X gate. So there's actually not just one cluster here. So we can threshold and we can give back 1 here, but there's actually kind of some kind of measurement based switching that's happening. So there's more complex behavior that's in quantum circuits that isn't that complicated to percolate up to the programmer and might be useful. So it's kind of an interesting thing to demo and show. So we have another qubit on this chip. We can run Quill code on multiple qubits. In this case, an X and a Y and an X and an X returns them both back to the ground state. And if we apply an X to one and an X half to the other, we run the random probabilistic demo live, and we wait. Oh, good. Yes. Made it easy for me. So it's pretty simple because you're working in Python to build up, in just a couple lines what state tomography looks like in PyQuil. So what you do here is you have some input program that you're trying to do tomography on. So this is the quantum circuit, and at the end of that circuit, you're going to apply all of your different rotations and measurements so that you can do the full tomography and get the density matrix. So those are the series of effects and preparations. I'll just click this off running because it's going to run a bunch of circuits. So we'll loop through each of these gates. We'll wrap them into a PyQuil program object. We'll append the program that we're trying to do tomography on. We'll just loop through them, and then we'll plot the data. So in this case, we're looping through each of these little, very, very tiny Quill programs, and then plotting. So here I ran the, let me just kick these off while I'm talking. Here we ran the identity gate. So nothing. And we end up in the ground state when we look at the results of our state tomography. And here I'm running the X-gate program, so we'll just do tomography on the excited state and get back the density matrix. Boom. And we can do the same thing with an X half. So the reason I wanted to show this is that Quill is actually really, really simple, and to some degree PyQuil is really simple. This looks like, in some degrees, a complicated stack. But I think there are ways of making this kind of programming simple enough that we can actually start to build on top of it the really complex tools that are needed to come up with new quantum algorithms that work, that show supremacy, that do things that people care about, and that are also valuable. So here's in this case, the tomography we get for the X over 2. So yeah, so as I said, it's pretty simple to use a Quil library to run single qubit circuits, to run things like Rabi. One thing that was interesting about the Rabi example we gave is we didn't tune up each of those gates separately. We just looped through the list and applied them using dynamically tuned up gates. We saw these additional IQ plane measurement physics, a little bit more information that can happen when you have physical qubits and that you might care about when you're programming things that are physical qubits. And we ran within a couple lines of Python quantum state tomography. But again, this is just the simple kind of building blocks, and I think what's really interesting about the stack and the kind of research tools that I think are really important for you guys are the applications and things that can be built on top. And this is Quil and Grove. And so for this, I'm going to turn over the lectern to my colleague, Nick Rubin.
Hi, everyone. I'm Nick. In the remaining 20 minutes or so, I'm going to go over two libraries that sit on the top of the stack. Will gave an introduction to how Quil and Quill can kind of be used to go down to interrogate what's happening with the physics below. And I'm going to talk a little bit about how to use the stack to go up and kind of study quantum algorithms and use the QVM simulator. So a little bit about my background. I'm actually a chemist. I specifically quantum chemistry and electronic structure. And so I studied methodologies to examine entanglement in molecules, specifically with variational 2RDM methods. And so what I'm going to talk about is what was the guiding principles in developing Quil and Grove. So before I jump into that, actually, what we're targeting, as Will mentioned, are near-term quantum algorithms. And so here's a list of some of the things that are in that family. When I mean near-term, I'm talking about devices that are between 3 to 100 noisy physical qubits. What lives in that area are variational quantum eigensolvers, specifically developed for chemistry, quantum approximate optimization, and then serving as a validation for error-correcting codes. And this kind of long, unruly list of citations is kind of just to show that there's a lot of work going on in this between industry and academia. Okay, so for the rest of this, I'm actually going to be jumping back and forth between the slides and some notebooks to demonstrate Quil and how we interact with the QVM. But just as starting off, this is the variational quantum eigensolver. And so at its core, variational quantum eigensolver is finding an eigenvalue of a matrix. It's very useful for very large matrices. And so really what it is, if you kind of look at it, is it's functional minimization, where you have some ansatz, and that ansatz is the wave function, and then you're using the quantum computer as a coprocessor to do expectation value measurement. This is sitting in a classical optimization loop, which is changing your parameters for that ansatz. So my pedagogical example is something actually quite simple. Let's say that we have an ansatz for a probability distribution that's a Gaussian, and you see this little video I have here. I have some Gaussian that I'm sampling from, calculating the expectation value against this quadratic function here, and then there's a classical optimization loop that is changing the parameters of that Gaussian, the mean and the variance. And so as we expect, it moves towards the center of this quadratic potential and gets very, very thin to minimize the expectation value. This is useful in quantum chemistry, now using something that's a little bit more complicated as our ansatz, a many-body expansion related to coupled cluster. And what Quil provides is a way to easily construct these things and then output Quill. And right here we have a short simulation of hydrogen binding. And so let me jump into the notebook to kind of describe some of the functionality of Quil. Okay, so just as a reminder, we're looking at, let me zoom in so it's a little easier to see. We're looking at these two top libraries at the top of this stack. So some things that you might want to do as a kind of if you're looking to develop algorithms. So commonly I want to encode some problem in some Hamiltonian and use that Hamiltonian as the generator for some unitary. One of the things that I might want to start out doing is representing the language of quantum chemistry, namely fermionic second quantized operators, into something in the Pauli group. One way to do that is the Jordan-Wigner transformation, which I write down here. And so we're just checking parity with these Z strings here and then doing a raising operator. And with Quil, we provide a little computer algebra package for Paulis that lets you easily construct something like this. And so here we're just doing a creation operator, and I'll just print through. And we see if we actually do a creation on 5, we do construct the correct object in the poly group. And so we have our Z string here and then our raising operator. But we can do much more complicated things. We don't have to just do something simple here. We can write down our favorite Hamiltonian, the Hubbard model. Though it is very simple, there's lots of, as everyone knows, there's lots of interesting physics. I wrote some helpers here to kind of do some, does this function here that does the creation annihilation operators. So that's just, I'll import that. And we can just directly write down our Hamiltonian. And so we go through these loops. We define how many sites we have. We define the interaction parameters for this thing. And we just fill up our Hamiltonian. And these are poly objects that are sitting in Quil. And we can see that if we print this out, we get the Hamiltonian represented as some poly sum, some sum of sums in poly group. Okay, so I mentioned that this was very useful for doing variational quantum eigensolver. And one of the things that we provide in Grove, our algorithm library, is functionality to do this. And so there's a lot of Python here, but what it's really doing, I'll just click through and then tell you about it, is doing a lot of classical preprocessing to things that are in chemistry, like molecular integrals and so on. But really all the functionality is there. And so I can represent my Hamiltonian by a bunch of polys, import some Grove, and then actually some modules from Grove, and then just run VQE as a loop. And here we're just doing this live. It's doing hydrogen at some particular separation. And then at the end, we get the correct energy. And you could look at reconstructing the state, sampling from this complicated thing. There's lots of stuff you could do. Let me jump back to the slides. Okay, so that Hubbard model I mentioned, I wanted to really just demonstrate that you can interface with a lot of other packages, you can do complicated things, you can easily go and pull data from other quantum chemistry packages. And so this is an example. This graph that just appeared is the linear Hubbard model looking at that unitary couple cluster ansatz versus the U parameter and the energy. And each line is a different method. So like mean field, classical couple cluster, unitary couple cluster, and then the exact solution. Another thing that comes standard in the library, specifically in Grove, is our implementation of the quantum approximate optimization algorithm. We have maxcut written by default as a module, but it also will accept any cost function and any driver. And so as people start playing with or borrowing ideas from the annealing community, we can look at driver Hamiltonians that commute with the cost function so we can encode constraints into that. And so this example here on the slide is just showing you max cut on a ring, or the ring of disagrees, at p equals 1, the shortest version of this. And so those two tall lines on the graph there are actually the correct bipartitioning of the nodes. And you can actually increase that and get the right answer. And this is all simulated with Forest and Quil. So this is just actually I'll jump out again and kind of show you that functionality that we actually have. One of the nice things about sitting in a Python environment is that you can easily construct any graph or any cost function with Quil and just use what we have. And so here I just generated a random graph, and out of that I can just print the circuit that you would get out from the QAOA algorithm. And so this is quite long, doing variational eigensolver with some minimizer is possible, and we can do this up to about 20 qubits on our QVM. And so this is the last example slide that I'd like to show. We've talked a lot about kind of simulating down, but I also wanted to kind of point out that we can actually go up and interface with a lot of other things that would use these as kind of or use this idea of a quantum computer as a coprocessor. And so one of the applications as a chemist I see is using variational quantum eigensolver or phase estimation with other quantum chemistry algorithms. And so one that we looked at was density matrix embedding. As a summary, it actually is just a way to take an arbitrarily large quantum system, discretize it, and actually figure out what the correct single particle effective embedding potential is. And so for the Hubbard model, you can study an infinite system and actually get very, very good answers. Another thing that you can do that we were just playing with was what is a good mapping between physical indices and qubits on your lattice. And so I showed you Jordan Wigner representing fermionic operators to some element in the poly group before. There are other ones that are out there like Rigetti. And what those do actually is posit a structure of connectivity of qubits on your actual quantum device. But that actually might not represent reality. Rigetti parity graph here actually doesn't represent a lattice of qubits that maybe is compatible with the surface code. And so what we noticed was that this actually lives in a family of transforms that you can use your actual qubit connectivity to represent the graph, the parity graph. And so we'll be putting that on, both of these things on arXiv soon. And just to show here, actually, the number of qubits on that, or the x-axis here is the number of qubits on the bottom. The y-axis is the gate counts, and we actually see that when you consider doing arbitrary entanglement on your lattice, you actually are saving by using this transformation, the transformation that's including information of the qubit layout. So here we're actually saving in the number of swaps that we have to do. Okay, so just as a summary, Quil lets you programmatically generate and manipulate Quill programs. It comes with a little computer algebra package, so you can easily do a lot of things like encoding your problem, simplifying polys, and things like that. It comes with Grove, and so there are some things that we've implemented in there, like a very flexible and robust version of variational quantum eigensolver, QAOA, and then the normal samples like teleportation, QFT, and phase estimation. And also manages your connection to the Rigetti forest. And so when you have your beta key, you can go and run on the QVM and eventually real hardware. And so just to be clear, this is actually really one of the reasons that I really like Python is that it has a lot of really large community and it's really easy to install. And so you can pip install. Here are the libraries. They're actually up now on PyPy. You can go get them. And I think we do have pretty good documentation, and we try to be very responsive to any issues that are raised. So I think with that, I'll turn it back to Will.
So this is the stack. We're going to throw you guys some notebooks in a second and a link to pull up some things so you can play with it yourself. But we want to take a quick break where we've got everybody to take, if you guys got questions now before you play with stuff, we're also going to be around to answer questions later. Anything? No? You guys just want to play with stuff? Yeah, what's up? Yeah, so we don't have a lot of gate circuit and compilation stuff. Yeah, I'll repeat the question. The question is, do you have circuit compilation or circuit optimization stuff in Quil now? And we haven't added that yet. We'd be happy to work with anybody to add that. If anybody has ideas about how to add that, which algorithms we should add, there's a lot of really great ones out there. We really want to. So yeah, on the QVM, up to about 20. Yeah, 20. Yeah. But if your circuit's really long, you'll notice. Yeah, so the QVM implementation we have now is doesn't do density matrix evolution. But if the one thing that's nice about having a Quill spec is that you know the spec for that. So if anyone wanted to write a density matrix simulator, which is one thing we're thinking about working on as well, but haven't had time yet, you know how to do that. That's something that we would find very useful to do mixed states. No, so it'll do a projective measurement. It'll just do a projective measurement on the one. Yeah.
I think there's a question over there.
Hey.
Does it keep the entire state around? Like is it a sparse state, the quantum state of your simulation?
Yeah, so it stores the whole state, but it applies it doesn't tensor up so this is about the QVM implementation. So the question is, does the QVM store the entire state? And a little bit about how the quantum virtual machine operates. So it stores the whole state, but it doesn't apply or tensor up all of the gates and unitaries. It applies the unitaries in place in kind of that typical sort of efficient way.
Okay, but it's like when you say you can simulate about 20,
Yeah.
on the paper, so does it actually store 2 to the 20 doubles or something? Or is it a sparse?
You want to answer more? Yeah.
Yeah, so the wave function representation is dense. It tries to be a little bit clever about looking at your Quill program. So if you're not using certain qubits, or if you decide to index your qubits in a certain way, it's going to use the minimum number of qubits possible. When we say 20 qubits, generally we're talking about just on a normal laptop, a normal sort of developer's laptop, not on any big cluster or supercomputer or anything like that. We do store all 2 to the n qubits, all the amplitudes, and generally we found that to be most useful as opposed to any particular sparse representation, because a lot of the computations that we're doing eventually is entangling all the state. So we found that the most practically useful thing.
But yeah, if any, I mean, one of the reasons for opening this up is people have ideas about how to write better simulators. That'd be great. Like, I think community-wise, if we had one really, really great distributed open source simulator that you could then build like kind of the more abstract programming tools on, that would be awesome. So anybody who wants to work on that with us, like, please talk to me. Yeah. Yeah, so we don't use it for everything. We're actually finding, as we were putting together, this is the first demo that we've done live of running qubits, and in putting together this demo, we've started to think that we're actually going to use it a lot more internally as our front end. It's sort of a bit of dog fooding. But for more complicated tune-up, things like gate septomography, stuff like that, we haven't done it through Quil. But we could, and I actually think we might just migrate to using this as the front end even for our experimental tune-up and calibration. Oh, yeah. Do you want to talk about recursion?
So the question was, can you implement recursion? So the Quill language itself doesn't include any notion of like a recursive function call. So that kind of brings the question, how do you implement something like QFT, which is recursive? This was part of the reason why we built PyQuil, is because, well, Python has this natural notion of recursion, of course. And implementing a circuit in PyQuil, a recursive circuit, is really sort of natural and straightforward. So actually, there's a good example of this in the Quill whitepaper that sort of uses the QFT as a primary example with sort of Python pseudocode that shows how to sort of recursively build up a circuit.
Yeah. Classical. Yes, if it's classical or quantum recursion, it's classical. Quantum recursion is hairy.
So for the quantum approximate optimization,
Yeah.
you said you can use different drivers. How much control do you have over the protocol, as in over the schedule you use, or can you start
Repeat the question.
on uniform superpositions or on the ground state driver?
So the question was whether how much control you have over the classical protocol, right? For the schedule.
Yeah, the quantum approximate optimization.
Yeah. So what we actually provide is a way to actually use any classical optimizer if you want to run the algorithm in that mode, and we do allow you to do any kind of order of the algorithm. So given maybe Suzuki Trotter version 1, you can do any kind of number of steps of that. And so what I showed was alpha 1, and then we jumped all the way to 5 for this example. But you could do it at any order. We do have functionality for doing other up to 5 fifth order Suzuki Trotter if you'd like.
And from like a structural standpoint, like one of the ways that these VQE loops work is you can put in any Quill program, any PyQuil program as your ansatz. There's no restrictions on what you put in. And we have this kind of thing, you can look this up in the documentation, it's too much to say now, but we have this notion of a parametric PyQuil program, which is like a template for a quantum circuit where you can then like variationally fill in parameters. And this comes in really handy. Cool. All right. So why don't you can pull out laptops now. And if we jump into the browser and you guys go to forest.rigetti.com/notebooks, you'll get access to a bunch of notebooks that show both, there's one that runs the Quill native code in it, there's things that run max cut, there's things that run VQE, and there's some kind of cool examples to play in. The sign-in is just your email, and the password is capital QIP 2017. So I can walk you through that. we'll see how much the conference internet holds up. There's also one more thing that I want to show you guys. So if you do not have your laptops with you, you can also tweet to run a quantum computation, either on the QVM or if you're me on the real thing. So @QuillBot is live on Twitter. If you do @QuillBot and give it a Quill program, it will run it for you. You can fit it in 140 characters and tweet back. If you're me and you tweet at it, it'll run on that same qubit, on that same chip that I was demoing earlier. So this is, oh, my syntax was maybe wrong? We'll find out. So this is the exact same thing I was running in the PyQuil notebook, but just through Twitter. So if you want to run and make a superposition state using my phone, using Twitter, come up and grab me, because that's fun. Also, if you guys need any help or if you have questions about what you're looking at in the notebooks, there's several of us here. We'll kind of disperse around. A bunch of my colleagues know this stuff really well. We've got drinks in the back. I think we're out of cheese. But at this point, ask questions and have fun. And thanks very much for your attention. So, cheers.